So we are talking about using activities to find answers to chemical problems. We've been finding answers to chemical problems without activities for a good long time, and we haven't really seemed like haven't had any trouble with it. But we haven't had life or death situations depending on this either. So if you want to really get the, I guess some people call it the effective concentration. If you have some compound, now does the compound have to have a charge? Yes. Otherwise, it doesn't make any sense. It doesn't matter whether it's concentration or activity then if there's no charge. So something has a charge. Some compound. Could be a conjugate acid, conjugate base, whatever. And it's got a charge. And if you want to know the effective concentration, who knows what this chemical environment is, right? But you keep track of all the ions. You find the ionic strength. You find the effective concentration of this compound. That's what activity is. You get a lot better answers with it. So we're going to do the exact same thing we did before. That's how this is set up, the way it is we're going to solve problems the exact same way we did before. If we used ice, we're going to use ice. All we do is just replace concentrations, what's in brackets, with what? The A's. Right. If it's a bracket, concentration of, call it X, right? Then you replace it with just a big A. But what if it was a concentration of an X is a bad example. Because we think of X as something else. Of compound A. No, that's even worse. Jeez. A B. Okay, so whatever the expression is, and it's a concentration of B squared, then you got to replace it with, in this expression, whatever it is, A squared. A little B down there, and a squared, right? And remember, sometimes we develop these ice. This is to give you a big picture. We do these ice tables, and remember, all your answers are in what row? The E row. Sometimes we get like a 2x plus 0.5, right? Who knows, right? We get something down there, and that is right under the B guy, right? So within our expression, we replace, and it's supposed to be squared. So we put 2x plus 0.5 in there, right? But now we're supposed to be using activities. No big deal. You just replace all the concentrations with activities. So you're going to still have this, but you're going to have that little activity coefficient squared out next to it. The fudge factor squared, that's all. So you're still going to solve for x, except you're going to have these little fudge factors next to stuff you have to worry about. They're just numbers. Right? The fudge factors, I'll give you the right answer. Take into account the ionic atmosphere. Okay, so let's mess with some of those. Here's the first one. Use activities to find the pH for each solution. Okay. Now, remember there's easy ways and hard ways to find pHs of acids, and you're just hoping it's a what type of acid? Strong acid. Hey, you don't have to write any Ka reaction. Nice, right? So before, we would just plug pH is a negative log of concentration of H. But now we can't use that anymore. We have to say the negative log of the activity of H, right? Okay. So that's the negative log. And remember activities, it's right here. All activities are the concentration times the fudge factor. Okay? So, concentration of H plus times its fudge factor. And the concentration, everybody, is 0.001. Here it is, right? Okay. This is getting awfully long here. Negative log 0.001. Well, times this whole thing here, and then times its activity coefficient. Okay, to find an activity coefficient, we need to know the ionic strength. And be in the table. Is it in the table?
Yes.
Okay. What do you look up for ionic strength? I see. I've made this question thinking you could find it in the table.
Oh,
So right. So you need to find this guy. And how do you find him? He's in this table, right? But we need to find ionic strength. What's the ionic strength of this solution? Yeah. Concentration times the charge. But there's that 1/2 out front. So if we did the work, won't we get 0.001? Yeah. Okay. I was thinking, ouch. I forgot about the 1/2 out front, right? So when can we not use this for ionic strength? When can we not use it? I think when it's not 1-to-1 salts. We'll see pretty quick doing a bunch of these problems. But they're not 1-to-1 salts. I think you got to do the whole math to calculate the ionic strength. Right? 1/2 times the sum of the concentration times the charge squared. Okay. But we're okay. It's a 1-to-1 salt. So you could go through all the work and find it, but you'll see that the ionic strength is 0.001. So now thank you. 0.967. Thank you. And then we go and find the pH. Right? 0.001. Get that. Take the log. About 3. Wow. And really, to make sense out of this, carries don't round to 3, right? The 3.01. Because they're going to want you to calculate pH with activities and without activities. And if you round this to 3, you're not going to see any difference. So you want to carry some digits there. Okay. But they're not asking that. They're just asking for use activities. How about for 0.001 molar NaOH? Have to what? You could use POH, find P, but we have to use activities. So using POH and then subtracting 14 to get pH isn't using activities. No. We need to use this. We need to find concentration of hydrogen ion. Not Kb. What is? Do you recognize what this is? Strong base. Thank goodness. So we know the concentration of what? OH. Because if it's not a strong base, then you got to do the whole Kb thing. But it's a strong base, so we know the concentration of OH is 0.001. Doesn't quite help, but if you know the concentration of OH, how do you know the H? Not doing the POH-pH thing. You could. And then you have to take the negative law. Yeah. Do you remember this one?
Oh,
yeah. This I think is the easier way to do it. Now you can do Pedro's way, right? Subtract from 14 to get pH, but then you have to raise both sides to what to get the hydrogen ion concentration? The 10 power, right? So there's going to be several steps there, and it's going to be kind of involved. Here it's not too bad, because Kw, you know, is 1 times 10 to the negative 14, and this guy was the 0.001, so we can find hydrogen ion. Oh, yeah. One times 10 to the negative 11. So we are going to end up with, for B, pH is the negative log of 1 times 10 to the negative 11, right? Times my ionic, my activity coefficient. But I need to know the ionic strength. The ionic strength is, again, 0.01. Okay. Now realize we are making an assumption here. Because it's not, you're supposed to add up the 1/2 times the sum of the concentration of the charge times this charge squared, the concentration of the charge squared, right, that ionic strength equation, for every single ion. We're not doing it for H+. Do you recognize that? But it's so dang small. You add this on, it's not going to do anything. So we're not worried about the H+. Just like over here, when we found our ionic strength, we weren't worried about the OH-, right? Because it's so minuscule. I mean, technically we should have. We should have had it in our calculation, but we didn't. So, what's my activity coefficient? It's going to be 0.967 again. Right? And get something really basic this time, I'm sure. 1 times 10 to the negative 11. Take that times 0.967. About 11. Wow, 11.01. Okay. Now I'm sure what's coming up in the homework, they're going to say, is that what's coming up next? No. Find the pH of this whole thing, 0.01 molar HCl, in 0.25 molar sodium nitrate, right? All you do is have to calculate the new ionic strength of everything using the ionic strength equation. So you'll end up with a different activity coefficient. Do you see that, what's coming up? Make sense? Well, we'll do some more. But I think I wanted to jump right to where it gets really confusing. It shouldn't, but it is. Using activities, find the concentration of barium in a 0.1 molar, I don't even know, quaternary something iodate solution saturated with barium iodate. And then I looked up the KSP of barium iodate, and there it is. Let's see. That quaternary compound there. Let's ask Kat. What does that have to do with anything? Look at this. What does this have to do with anything? If that wasn't there, just ignore it. This would be a straight what type of problem? KSP problem, right? Because the concentration of barium, I mean, if we find our X in ice, we can look at our ice table and see and get the concentration of barium, right? So this is a solubility problem. What does that quaternary compound have to do with anything? Even though it looks complex, just look for what? Look for... It's the initial concentration of IO3. It's a common ion effect problem. So when they have these complicated things there, all you're really looking for is there a barium? Look at what the solid is. Is there a barium or is there an iodate? If there is, then you have something to put in your initial row. Otherwise, there's nothing there. So that's really all you look for. But now we're also concerned because now we have to do ionic strengths and find the, know what all the ions are, know what all their concentrations are in the problem. So it's also going to play a role there. So now we really have two worries. We got to look for these compounds that they just throw in there, it seems randomly. Look for a common ion, no matter how ugly it is, but also realize, ooh, he's a salt, he's going to play a role in calculating the ionic strength. Okay. But it all starts with this KSP idea. So we treat everything exactly the same we did before, Adriana. We're going to do everything exactly the same way we did before. We're going to get some relationship in terms of concentrations. KSP equals these concentrations. All we're going to do is replace the concentration with activities, right? But see if you can get us there. Where do you start?
Start with
The reaction. And that is
barium
iodate.
iodate.
Yeah. So remember, the solid always goes on where the reactant is. Right? And that goes to, she got you started, John? That goes to what? Ba plus 2 and what? 2 iodates. Exactly. Okay. And then, Kathleen, we're supposed to do ice if it's solubility. Solubility is the X in ice. They didn't ask for solubility, but they're asking for a concentration of something, so it is a solubility problem. What would you do now? Yeah, put all the dashes on the solid. All right, good. They never show up in equilibrium constant expressions. Pedro, now what? Follow what he's saying? He's right. He's dead on. That iodate, it's a 1-to-1 salt. It looks ugly, but it is. It's a 1-to-1 salt. So the concentration of iodate in the beginning is 0.1. Okay. Under the barium, nothing there initially. Okay, Danielle, now what? The x's. So you'd have an x and a 2x. Add everything up. We get an x and a 0.1 plus 2x. Okay. Your Andy, now what? Yeah. The KSP, that equals concentration of barium times squared. Good. Right? I like that she said this, because now we know we're supposed to use activities, so it'll be a lot easier to substitute now. So we're really supposed to write, cross this out, we're really supposed to write A with a Ba plus 2 and another A with a iodate. Okay, but that guy needs to be squared. Okay, so now let's substitute in what activities are. Right? Activities are Pablo. And you misspelled your name, Pablo. Okay. Hear that? Whatever. Okay. What would you do right now? Wait, don't put them in yet. Let's just write. Well, we could. We could. Yeah, why not? Because he knows. You've done this a lot, right? The concentration of barium is X. Good. All right? Times. Remember, it's activity, though. So that activity coefficient thing, right? All right. We could have squeezed them in over here, right? That little activity coefficient of barium, the activity coefficient of iodate squared, but that's okay. And then we're going to have whatever, let's pick on somebody. Miriam, now what? Oh, yeah, the iodate, so you're going to put in what? 0.1 plus 2x. And the coefficient. Okay, we just forgot one thing. What'd you forget? Square this guy, right? Because it has to be the concentration of iodate, which is this. Concentration of iodate's the 0.1 plus the 2x. That's my concentration of my iodate. So that has to go there. Yep.
Do you get rid of the 2x?
We will.
Oh, okay.
And remember, what's the question we ask? Nylon wants to drop this 2x already. Yeah, all you do is you look over. Oh, we didn't write it down. There it is. 10 to the negative 9. We're good. We can drop it. Let's find out what these activity... we have to put in numbers for these fudge factors, but we can put that in. She wants to put that in. We can do that. 1.5 times 10 to the negative 9 has to equal, well, approximately, x... Well, let's figure out what those fudge factors are, right? She's right. We're going to be dropping this 2x. But let's see what these are. So we'll have X times the activity coefficient of barium. Okay, so we find them in the table, but we need to know the ionic strength to do this. Let's see, where's my, oh, here's my table. I can just find it here. Here's barium. Okay, what is my ionic strength? What is my ionic strength? What are all the ions I have to worry about? I've got to worry about the barium. I have to worry about the iodate. And this funky salt over here. Right? So I have to use that equation 1/2 the sum of the concentration of the charge of each ion squared, add them all up. But you notice some I'm not going to worry about. Which one have we mentioned? We're not going to worry about them. He's going to be really, really, really tiny. In fact, we don't even know what it is. The barium, we don't even know what he is. But he's going to be really, really tiny. Look, 10 to the negative 9 equals the stuff times X. X is going to be really, really tiny. And X is barium, so we're not going to worry about him. Plus, we don't know what he is anyway. So, what is going to be our ionic strength? So all we know about what's left over, this isn't an ion. This guy and this guy. These are 1-to-1 salt. Ionic strength has to be 0.1. Huh? Right? It looks weird, doesn't it? But it doesn't really matter what this thing is. You look, there's only one IO3. There's only one of these things, so it's a 1-to-1 salt. No matter how ugly it is, it's just a 1-to-1 salt. So our ionic strength is 0.1. So we can look up here, find 0.1, and my barium. Oh, he's down here. Right? Danielle, that makes sense? Okay, 0.38. Okay. And so our ionic strength, we just got it right from the salt, because the only other ion there is the barium. He's got a +2 charge, but his X is going to be really, really tiny, so we're not going to worry about him. So we can say, Nyla, we can say this is now approximately 0.1, but don't forget to square them. And now I have to find iodate. He's negative, plus or minus the 1, right? See how you look at the plus or minus the 1? It helps you find them. Oh, there he is. So he's got to be, what number? 0.775 is how they want you to read it. Right, 0.775. And don't forget to square it. Good. We go through all the work. We find our X. And then we go back up and see, what were they after again? Oh, they're after barium. You look in your E row to see what the relationship is between X and the concentration of barium. And according to our E row, X is barium. So we don't have to multiply by 2. We don't have to add anything. We just, X is our answer. Okay. Let's see. Negative. Divided by 0.38. Divided by 0.1 squared. Divided by 0.775 squared. I got about 6.6 times 10 to the negative 7. Oh, good deal. Okay, so that's what I got for X. And that is my concentration of barium, according to my table. See, so we didn't need him. We didn't need him when we were calculating the ionic strength, because he's extremely small. Okay. So you see the game plan? If it's a solubility problem, if it's a pH problem, it doesn't matter if it's a Ka problem, Kb problem. We just determined what type of problem it was by what they gave us. Here they gave us a solid. It's a KSP problem. If they would have said, I don't know, it's HF and they want to know the pH, well then you got to write a Ka expression. If it was sodium cyanide, then it would be and they want to know the pH, it would be a K. Did you follow that? If it's a sodium cyanide, 0.29 molar sodium cyanide, that's a Kb problem. They want to know pH, right? Because you recognize the cyanide, you have to look up the Ka for HCN. Okay, so we do the exact same thing we did before, all the same work, and just get our expression with the K, and in terms of our X's, but just don't forget we have to insert those activity coefficients in there, and it's exactly the same problem. Okay, find the activity coefficient, 11 here. Find the activity coefficient of H plus in a solution containing 0.01 molar HCl plus 0.04 molar KClO4. What's the pH of the solution? So first they want the activity coefficient. Right, and then we'll find pH. Dang, I think they're being too nice, Amanda, on this homework. I think they're being too nice on the homework because we don't have to do any real trouble to get these ionic strengths. At least that's what I'm seeing. How are you going to get the, right, to look up the activity coefficient, Amanda, we got to find the ionic strength.
Yeah, so you use the concentration or charge of each ion inside by 2. Like,
Whoa.
So like it's 0.01, it's concentration of each of those.
And then, yeah.
0.04 is concentration.
So our total ionic strength would be 0.05. Did you follow all that? We might want to prove it to ourselves. Right? We might want to prove it to ourselves. We're saying that this is HCl is a 1-to-1 salt. Ionic strength is, you get 0.01 from that. This is a 1-to-1 salt. Ionic strength is 0.04. Well, the total ionic strength would be 0.05. But if you don't see it, we might want to prove it to ourselves. Ionic strength is 1/2 sum concentration times the charge squared, right? Add all that stuff up, right? 0.01 times a positive 1 squared, 0.01 times a negative 1 squared, right? Just to prove it to yourself. I think you need to. Otherwise, you're not going to be comfortable doing this. See how these ones are saving the day. If you didn't have, right, I guess we need to be more specific than a 1-to-1 salt. We need to say a salt that has what charges? Positive 1 and a negative 1, right? Because you could have a 1-to-1 salt isn't, yeah, -2 to +2. I'm trying to think of something that's completely soluble that has a -2 is it? Well, then maybe there is. I can't think of one. And then you have to do the same for the other guy. You have 0.01. Potassium's positive 1. You have 0.01 perchlorate is a negative 1. All right. So you figure all this out, and you, all right. Oh shoot, that's a 4. That's a 4. Yeah. So we're adding it, and then we're dividing it by 2. I mean, they get the same thing. So it's just 0.05. Our ionic strength is going to be 0.05. So that means that our activity coefficient is, what is it? 0.86. Okay, so we have that. What's the pH? What's the pH? Negative log of the activity times the concentration. .86 times what's my hydrogen ion concentration? 0.01. See, this stuff isn't going to be too bad. About 2.06 or 2.07 or so. Not too bad. All right. So you have a handout in addition to the homework. Might as well get started on it, right? We have about 4 or 5 minutes. See how far you can get on this. So we want to find the concentrations of mercury 1 ion and mercury, well, they call it mercury 1, yeah. Oxidation stage 1. Mercury 1 in the saturated solutions of mercury 1 bromide. I looked up the KSP for you, so it's up there. Because now the only reason to give you the KNO3, if it was not there, I don't see how you could do an activity problem because you would have no idea what the ionic strength is. That's all it's doing. Exactly. Now you got to be careful though. You want to make sure, look for the common ions, but there aren't any. So you're covered there. And then Amanda's wondering, well, why is it there? There's no common ions there even. It's all for ionic strength. Exactly. That's the only reason why it's there. So it can give. So you know what the ionic strength is. So you know what fudge factors to look up in that table for activity coefficients. That's the only reason why it's there.
So you have to do the concentration of the K times its charge times the concentration of NO3 times its charge plus the concentration of H.
Well, if you want to get ionic strength,
right.
You're right. You have to identify all the ions, including the bromide and the Hg2. However, realize that, look at that KSP. If you wrote up the whole KSP reaction, you're going to see those X's are going to be extremely small. So that means that concentration of mercury 1 and that concentration of that bromide, they're going to be 10 to the negative 23. They're going to be extremely small. So you don't have to worry about them. The only ions you need to worry about for ionic strength are going to be the potassium and the nitrate. And it's a 1-to-1 salt, so ionic strength is 0.01. Yep. So I would write out so you don't screw up, I'd write out the KSP reaction, fill out the ice table, right? Even though you may not need to. If you don't, fine. But substitute in for the concentrations in that KSP expression, substitute in activities. But this is going to be extremely small. These ions, their concentrations are extremely small. Because the KSP is 10 to the negative 23. So the concentration of these guys are like X in ice or 2X in ice. X is going to be extremely small. All your ionic strength is going to be just from that KNO3. Oh, you can, yeah, you can. You could calculate it, but it's going to turn out to be 0.01. So if you're not sure where to start, just ask. Okay, so I would start by writing, first you recognize the question. What type of, forget the whole activity thing. What type of question is this? A KSP problem. So you write out the KSP. The only time activities come into play is at the very end. when you have these nice concentration brackets written out and you're ready to solve the problem, you just stop yourself, cross out the concentrations, and write an activity, a big A instead. Everything is the same.
So there's no initial concentration?
No, because there's no common ion. Yeah. All right.
That's not an addition, that's just extra.
So just start out by writing the KSP reaction. Fill out the ice table. All right. And the KSP is that number. It's equal to products over reactants. Oh, we're running out of time. All right, let's make sure you're following here.
Well then.
Right, this is how you write a KSP reaction, right? A solid goes to its ions. That's not a solid. Right? Right, hopefully you have that. Everyone agree? And then you do ice. And X and 2X. Right? Okay. So now we do 5.6 times 10 to the negative 23. Just don't go in terms of X's right away. Yes? Mary? No, this guy stays together. Look at that. The only reason why I did that is look how they wrote the mercury. That's the ion it has to go to. Right? You have to go by the ion they want. Right? And that's going to be the activity of 1 of the Hg2 plus 2, the activity of the bromide squared. Now you just substitute in, right? Concentration times his activity, concentration times his activity. Okay? So come by. I'll be glad to help you out with this stuff. You get used to it after a while. Just got to keep at it.